At the end of the topic, you will be able to know about a circle and its parts, state and prove theorems on circles.
A circle is a plane curve consisting of all points that have the same distance from a fixed point, called its center. The common distance of the points on the curve from the center is called its radius. There are innumerable radii in a circle. The length of a line segment whose endpoints lie on the circle, which passes through its center, called its diameter. The length around a circle is known by a special name called the circumference. In the figure, O is the center of the circle, OC is the radius of the circle, and AB is the diameter of the circle. Let us see the chords of a circle. The line segment joining any 2 points of a circle is called a chord. A chord passing through the center of the circle is called the diameter of the circle. The diameter is the longest chord of a circle. Just like radii and diameters, a circle has innumerable chords. In figure, AB, ST, PQ are the chords of the circle. PQ is the longest chord, which is known as the diameter of the circle. The points P and Q divide the circle into 2 parts. Each part is called an arc. The arc PYQ is called major arc, and the arc PXQ is called minor arc. The area bounded by 2 radii and an arc is called the sector of the circle. The sector with minor arc is called minor sector, and the sector with major arc is called major sector. In the figure, OPXQ is the minor sector and OPYQ is the major sector. A chord of a circle divides the circle into 2 parts. Each part is called the segment. Region bounded by the chord and the minor arc is called the minor segment. Region bounded by the chord and the major arc is called the major segment. If the chord divides the circle exactly into 2 halves, then they are semicircles. Look at the circle. The shaded portion of the circle is the interior of the circle, and the outer portion that is not shaded is the exterior of the circle. Points which lie interior of the circle are called its interior points. Points which lie exterior of the circle are called its exterior points. Points which lie on the circle are called its boundary points. There are innumerable points in the interior, exterior, and boundary of the circle.
2 or more circles having the same center and different radii are called as concentric circles. In the figure, O is the center of the concentric circle, and OA, OB, OC are the different radii, and OA is less than OB, which is less than OC. Circles having equal radii are called congruent circles. In the figures, AB is equal to CD. Thus, the circles are congruent circles.
Congruent arcs. If 2 arcs of a circle are subtended by the same angle at the center, then the arcs are said to be congruent arcs. The figure shows a circle of center O along with 2 diameters AD and BC. Since the angle AOB is equal to the angle COD, it implies the arc AB is equal to the arc CD. Thus, arc AB and arc CD are congruent. Similarly, angle AOC is equal to the angle BOD. This implies that the arc AC is equal to the arc BD. Thus, arc AC and arc BD are congruent.
Let us learn about circle and a line in the plane. Consider a line and a circle. There are 3 possibilities that arise. A line may have no common point with a circle. A line meeting a circle in exactly 1 point is known as a tangent. A line meeting a circle in exactly 2 points is known as a secant. Let us discuss another theorem. Congruent chords of a circle subtend congruent angles at the center. Click on the proof button to view the proof. Let us see the converse of the previous theorem. If the angles subtended by the chords at the center of the circle are congruent, then the corresponding chords are congruent. Let us prove the next theorem. The perpendicular drawn from the center of a circle to a chord bisects the chord. Click on the proof button to view the proof. Let us see the converse of the previous theorem. The segment joining midpoint of a chord and the center of a circle is perpendicular to the chord. Click on the proof button to view the proof.
Theorem 5. Equal chords of a circle are equidistant from the center. Click on the proof button to view it. Theorem 6. Let's prove the converse of the previous theorem. The chords of a circle which are equidistant from the center are equal. Click on the proof button to view it. Here is the next theorem. The angle subtended by an arc of a circle at the center is double the angle subtended by it at any point on the remaining part of the circle. Click on the proof button to view it. At the end of the topic, you will be able to
define cyclic quadrilateral, state and prove theorems on cyclic quadrilaterals.
A triangle inside a circle is the most familiar geometrical figure. But triangles aren't the only shapes that can be fit inside circles. Even four-sided shapes like quadrilaterals can be fit inside a circle. But not all quadrilaterals will have all four corners touching the circumference of the circle. Quadrilaterals that do, however, are known as cyclic quadrilaterals. In this section, you will learn more about cyclic quadrilaterals. Let us move on to concyclic points. Points lying on the same circle are called concyclic points. For example, the points A, B, C, and D are concyclic as they lie on the same circle. Do you know what a cyclic quadrilateral is? A quadrilateral having its vertices on a circle is called a cyclic quadrilateral. It is clear that the vertices of a cyclic quadrilateral are concyclic. In the picture, ABCD is a cyclic quadrilateral. Let us have a look at a theorem based on cyclic quadrilateral. The sum of the opposite angles of a cyclic quadrilateral is 180 degrees. That is, the opposite angles of a cyclic quadrilateral are supplementary. Click on the proof button to view the proof. Here is the converse of the previous theorem. If the sum of any pair of opposite angles of a quadrilateral is 180 degrees, then it is cyclic. Click on the proof button to view the proof. Next, let us have a look at a theorem based on cyclic quadrilateral. The sum of the opposite angles of a cyclic quadrilateral is 180 degrees. That is, the opposite angles of a cyclic quadrilateral are supplementary. Click on the proof button to view the proof. Let us now look at an example. In the figure, triangle PQR is an equilateral triangle. Find angle PSQ and angle PTQ. Click on the solution button to view the